So, ladies and gentlemen, you are welcome. So, this is actually another question that we are going to solve. Question 5. The heat of combustion of ethylene at 170 degrees centigrade and at constant volume is minus 100, minus 300. We have minus 332.19 kilocals. And then calculate the heat of combustion at constant pressure considering water to be in liquid state. So you see here, we have the heat of combustion at constant volume. So we are now going to bring the data out from the calculations. We are now going to bring the data. So now the heat of combustion of ethylene at this temperature is equal to, so the heat of combustion, that is the internal energy of the combustion, is now equals to minus 332.19 kilocal. And then the temperature is given as 170 degrees centigrade. Then we have to convert this temperature from degrees centigrade to Kelvin. And how do we do that? We are now going to say, okay, the in the temperature in Kelvin is now going to be 273 plus 170, and this will give us a total of, if we now take this and we add them together, it is going to give us 400 and, okay, let me just use my calculator to get the answer. So we are now going to have, where is my calculator? So I have my calculator here. So we now have this 273 plus 1 plus 170. So we have 443. So now we have 443 Kelvin. So this is for the temperature. So we need to actually drive the equation for the heat of combustion. So how do we drive the equation of heat of combustion? So we know that actually when we say combustion, it means the burning of substance or the burning of hydrocarbon in the presence of oxygen to generate carbon dioxide and water. So usually during the and then we also have our R value. The R value already, as we can see, R here is equal to, we have 2 calorie per degree per mole. So we have also the value of R. And remember, ladies and gentlemen, we have a formula that gives us the relationship between internal energy, the work done, and enthalpy. And of course, the formula is, I think if you can remember, from, we have different law of thermodynamics, and I think you need to go back and watch my video on thermodynamics. I actually stated all the 3 laws of thermodynamics: the first law, the second law, the third law, and even the zeroth law. So if you watch my video on thermodynamics, you'll have an idea of this law of thermodynamics. And then very importantly, ladies and gentlemen, we have a formula that show the relationship between the enthalpy, the internal energy, plus the work done. But remember, the work done is depend. It can be the work done by the system or work done on the system. But remember, work done, it can be CV, but CV is equal to nRT. So we can now substitute the W here with nRT. So we can now have the internal energy, or the enthalpy is equal to internal energy plus. So we are now substituting W with nRT. So this is equation that trying to demonstrate the first law of thermodynamics, which said that energy can neither be created nor destroyed, but it can change from one form to another. So I think in so many of our videos that we are going to solve so many first question paper, as we are going, we'll be taking these questions one after the other. And I would like you to so I want you to understand, as we are doing this video, or as we are solving so many of these questions, we will be coming across most of the things that we talk on the concept of thermodynamics. And if you want to watch my video on the thermodynamics and the laws of the thermodynamics, the video is still in my YouTube channel. I can even add it to the comment box of this video so that you will appreciate it. But this is how to solve so many of the questions from here. So as we can see here, we now substitute delta H is equal to delta U plus nRT. So as we can see clearly here, we have the change in internal energy as this, and then we are also to calculate the heat of combustion at constant pressure. So it means that at this point we are to calculate delta H. So very importantly, ladies and gentlemen, at this point, this is the number of molecules. So the number of molecules can be delta N. So therefore, we need to now bring the equation. So when we say ethylene, it means ethene. So we have C2H4. So when it bonds in the presence of oxygen, generally, remember in combustion reaction, whenever we said combustion reaction, it means it's the burning of substance, like in this case, hydrocarbon, is the burning of hydrocarbon in the presence of oxygen to produce carbon dioxide and water. So generally, whenever you have a combustion reaction, you have your hydrocarbons and it reacts with oxygen, it usually gives us carbon dioxide. And then the next thing is for you to balance the equation. So let's see here, we have ethylene react with oxygen to produce carbon dioxide, and then from here, we are now going to balance the equation. So let's see. So here we have carbon dioxide plus water molecule. But the thing is that how many carbon do we have here? We have two here. So we have to add two here. So we have two molecules of carbon dioxide. And how many hydrogen here? We have four. So we have to add two here. So meaning that now for oxygen, we have two here, we have four, making six. So we are now going to add three. But remember, from the questions, we are to consider water as a liquid state. So therefore here we have L. But this delta N, it is just trying to show the number of moles of gaseous substance. And of course, as we can see, when we say delta N, it means the number of moles. It means the number of moles of product minus the number of moles of reactants. So as we can see here, we have 1 mole, and here we have 3 mole. And of course, we are not considering water because it is liquid. So therefore, here is 2 mole. So therefore, in the in the reactant, we have 4 mole in total. And then in the product, we still have 2 mole. So what are we going to do here? It's simple. So we are now going to get the value of N here. So now the number of moles of product is 2. So minus 4. We now have minus 2 moles. And then now we have our delta H here, which we are going to calculate. And we have delta U as minus 332.19. And then, of course, we have plus in bracket. The 2 here is minus, then times the R value is still, we have the value of R is 2, and then times the temperature. And the temperature, if you could remember, ladies and gentlemen, is 443. It's 443 Kelvin. So then the next thing now that we are going to do is we are now going to multiply this thing in brackets. But remember, this one is in kilocal. So we have to also convert everything that is here in kilocal. And how do we do that? We have to do it Like, okay, now, uh, these two is in cal. So we have to convert it to kcal. So how do you convert this to kcal? We divide it by 1000. So therefore, if we divide this by 1000 here, instead of using the 2, so it's going to be something like this. So because this one is in cal, so we have to make everything in kilocal because this one is also in kilocal. So how do you do that? We have to, when we want to change something to kilo, so we have to multiply, we have to divide it by 1000. So therefore here is something as 2 times 10 raised to the power of minus 3 kilo per degree per mole. I hope you understand. So here we are now using 2 times 10 raised to the power of minus 3 times 443. So when we now multiply this and everything already here we have minus, this is going to give us minus 333.96 9626 Kelvin. Sorry, kilocal. So now, which of the option suits our answer, ladies and gentlemen? So which one is? I think this one. So B is the answer. B is the answer. So I hope you appreciate this, ladies and gentlemen. Please don't forget to subscribe and join my YouTube community as we are going to upload more videos. Thank you very much.